Hi, I'm Tyler Johnson.
And I'm Katrina Hansen. And I'm Jillian McDonald, and in this lab we'll be exploring how passive filters work. In our overall setup we used a frequency generator set on the voltage controlled oscillator input, which produces a frequency scan controlled by the DAC. The DAC has inputs AI0 and AI1 to read in the voltages from the circuit at the input, as well as after the resistor for the low-pass filter and the capacitor for the high-pass filter. The A0 channel provided a voltage sweep from 0 to 5 volts to the frequency generator.
Here is our low-pass filter circuit. It is simply an alternating voltage source from the frequency generator. This then goes through a 1K resistor followed by a 1 microfarad capacitor in series.
Here's our low-pass circuit. We can see that it's low-pass because the resistor comes before the capacitor after the voltage source, and our resistor is 1 kilo ohm, our capacitor is 1 microfarad, and we set up our circuit to run an AC sweep from 11 Hz to 10 kHz at 100 points per decade. We see that on the low-pass graph, at low frequencies the output is about the same as the input, 1 volt. Then as frequency gets higher and higher, the output drops to about 0. We calculated omega naught to be 1 kHz, so we expect the voltage to be 1 over the square root of 2, or 0.707 at the 1 kHz mark. However, we see from this box here that it actually occurs at a frequency of about 160 Hz. And this is because omega is the angular frequency, and the graph shows a frequency of f, meaning that the values differ by a factor of 2 pi. However, we still see that the phase is accurate according to our calculations and is at about negative 45 degrees.
We built a VI in LabVIEW to observe how the changing frequency affected the input and output voltages. We made two different indicators on the front panel of the VI, a continuous chart and a Nyquist plot. The chart shows that the output, which is white, decreased as the frequency increased. By changing our time scale, we observed that the output was lagging by a phase difference of negative 90 degrees from the red input signal. The Nyquist plot for the low-pass filter should show an arc in quadrant 4 to reflect the negative angle of the phase. Unfortunately, we did not invert our signals when generating our VI and therefore have a graph that is opposite to our desired result.
Our high-pass filter circuit is the same as our low-pass filter circuit, except that the capacitor and the resistor have been switched.
And here we have our high-pass circuit because the capacitor comes before the resistor after the power source, and we still have a 1 microfarad capacitor, a 1 kilo ohm resistor, and the AC sweep settings are the same as the low-pass circuit. If we pull up the high-pass graph, we see that opposite to the low-pass filter, at low frequencies the output is about 0 volts, and as the frequency increases, the output reaches about 1 volt. For the high-pass filter, when omega equals omega naught, we still calculate the same magnitude of 0.707 volts, but the phase should be positive 45 degrees, as seen in this box here. And on the graph, this occurs at a frequency of about 160 Hz again, instead of 1 kHz, due to the factor of 2 pi.
The VI run for our high-pass filter circuit shows the output voltage signal increasing as the frequency increases. This is what we would expect since high-pass filters pass through high frequencies and block the low frequencies. Decreasing the time scale shows that the input and output signals are in phase. Our wave function appears jagged because we used a small DAC, which did not allow us to take enough samples to generate a smoother curve. Again, our Nyquist plot is flipped, which we know because high-pass filters have positive phase differences.